This is the AS2 paper from January 07, question number 2, and it's focused on refraction. First part of the question, state in words Snell's law of refraction. Okay, the first part of this definition then should focus on what Snell's law of refraction applies to. And it's at the boundary between two media the ratio of the sine of the angle of incidence and the sine of the angle of refraction is a constant. We also now know that that constant is called the refractive index, but you don't need to put that in as part of your description. There's 3 marks for that description or definition of Snell's law. The first mark is for stating what it applies to. At the boundary between two media is your first mark. The idea of the ratio of the sine of the two angles gets you your second mark, and that ratio being a constant gives you the third mark. So you need to be very careful if you've got all 3 elements in there. What it applies to, the ratio of the sines, and the fact that the ratio is a constant. Part 2 then. A ray of light is incident on a certain glass block of width 105 millimeters, as indicated in the diagram. On figure 2.1, sketch the path of the incident ray as it is refracted through the glass block. Label the angles of incidence and refraction on entry and show how the ray emerges from the block. So there are several elements there that we have to remember. We have to label the angles of incidence and refraction on entry, so with this side we have to label and show how the ray emerges from the glass block. Well, first things first. In any case for refraction, you must draw a normal. Use your protractor to draw the normal. Don't just estimate it with a ruler. And put a dot at either end, and then with your ruler carefully draw in the normal. Make sure that it's at 90 degrees. And to be sure, I would label that as normal. Okay, so first thing, we have to label the angle of incidence and refraction. Well, we can already start with the angle of incidence, and the angles are always labelled and measured to the normal. The normal is our reference. To draw the refracted ray then, we lay the ruler on. As the ray enters the glass block, it is bent or refracted towards the normal. So it means that this angle becomes smaller. So turn your ruler until it becomes smaller. Significantly so. Okay, let's remove the ruler. Before we go any further, we're still working on the labelling at the entry. So the angle of refraction again is to the normal between the refracted ray and the normal. Now we have to show how the ray emerges from the block. So again, we need another normal at this point at 90 degrees. And don't draw too small a normal. Makes it difficult for labelling. So make your normal significant. And then, as the ray leaves the glass block again, it is refracted away from the normal. And it's refracted at such a degree that the emergent angle is the same as the angle of incidence. Therefore, you could say that the incident ray and the emergent ray are parallel. So to ensure that you get that parallel, you could measure it with your protractor and draw it again at the same angle. Or if you're finding that it's tight for time, you can slide your ruler across, and very carefully, a little bit further. No labelling is required You only have to show how the ray emerges from the block. But so far, all we have is a series of lines and labelled angles. These are not rays until you have arrows added to them, both within the block and after emerging from the block. There are 2 marks for that diagram. The first mark is for the labelling of I and R, having drawn your normal with the correct refraction and arrows. The second mark is for your incident ray and your emergent ray being parallel. Now moving on to part 3 of that question. The angle of refraction of the ray when it enters the glass block is 32 degrees. And this ray takes 6.81 by 10 to the minus 10 seconds to travel through the glass block. Calculate the speed of light in the glass block. Well, our equation for calculating speed is distance over time. Now we know the time, we're given that in the question. We have to find the speed, so we must have some way of finding the distance. Let's go back to our diagram. In the diagram, we have the refracted diagram. We're told that this angle is 32 degrees. Okay. The distance the light travels is the hypotenuse of a triangle. We know that this distance is 105 millimetres, or 0.105 metres, and we want to find the actual distance travelled by the light, so we want to find this hypotenuse. I'm going to call it x. Whenever we're considering these diagrams, to find the distance x, we must use trigonometry. We have an angle, we have one side, and we want to find the second side. Looking at the diagram, this 0.105 is adjacent to the angle, and the x that we're interested in finding is the hypotenuse. So to use the adjacent and the hypotenuse, we must use cos. So back at our question, cos of 32 is equal to the adjacent, which was 0.105, divided by the hypotenuse, which was x. So we can work out that x equals, rearranging it, 1.05 divided by cos 32. And when you calculate that, you will find that x is 0.1238. So that is the distance that the light travels inside the glass block. So to find the speed, we take the distance, 0.1238, divided by the time, which is 6.81 by 10 to the minus 10. And when we calculate that, we find that the speed of light in the glass block is 1.82 by 10 to the power of 8. 1.82 by 10 to the power of 8. Now that does sound like a sensible value to us, because we know that the speed of light in air is 3 by 10 to the power of 8. So we're expecting a value of that order when we do that calculation. So we can always have this checking mechanism as we work through a paper. Moving on to part 4 then. Calculate the refractive index of the glass block. Well, in the previous question we calculated the speed of the light travelling through the glass block. We know that the speed of light in air is 3 by 10 to the power of 8. So the equation we're going to use is n equals c1 over c2, where c1 is the speed of light in air, 3 by 10 to the power of 8. c2 is the speed of light in the glass block that you calculated, 1.82 by 10 to the power of 8. And when you calculate that, very straightforward, that works out to be 1.65. The next part of the question then. State what is meant by the term critical angle. There are 2 different ways of describing this. I'm going to give you both. The first one is to say it is the angle of incidence which gives an angle of refraction of 90 degrees. So it's the angle of incidence at a glass air boundary which gives an angle of refraction of 90 degrees. Or you could say it's the angle of incidence, which, if exceeded, total internal reflection occurs. And either of those explanations is acceptable in the mark scheme. And it now asks you to calculate the critical angle for diamond, which has a refractive index of 2.1. To calculate our critical angle, our equation is n equals 1 over sine c. Therefore, c equals the inverse sine of 1 over 2.1. And that gives us a value of 28.4, which is much lower than the critical angle for glass or perspex, which is why diamonds sparkle so much.